Hello, everyone. Welcome to today's live broadcast, The Power of Polycapillary Optics and Their Critical Role in Seeking Life on Mars. I'm Laura Bush, the Editorial Director of Spectroscopy, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by Spectroscopy and sponsored by XOS. XOS is a global leading provider of advanced optics and OEM subsystems that greatly improve the measurement speed, precision, and sensitivity of X-ray analytical instrumentation. XOS's polycapillary optics can be used in many applications, including plating thickness, forensics, cultural heritage, and elemental mapping, such as on the Mars 2020 rover, where an XOS polycapillary optic will play a critical role in the search for past life on Mars after it lands in 2021. FlexBeam, their latest compact X-ray generator solution, combines a low-powered X-ray source and precisely aligned polycapillary optic to deliver a bright X-ray beam for advanced material analysis. The innovative optic mounting and alignment design enables an easy X-ray tube or optic replacement, making it a user-friendly tool for both OEMs and end users. Before we get started today, we have a few housekeeping announcements. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, and you can find those on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. Before I introduce today's speaker, I'd like to ask our audience to participate in a few brief polling questions. In each case, please click directly on the screen to enter your answers. So here's the first question. The polycapillary optic used in the Pixel system on the Mars Perseverance rover allows fast X-ray analysis on small features with a low-powered X-ray tube. Can you guess the power level of the X-ray tube used? 0.02 watts, 0.2 watts, 1 watt, 5 watts, or 50 watts? So once again, the polycapillary optic on the Pixel system on the Mars Perseverance rover allows fast X-ray analysis on small features with a low-powered X-ray tube. Can you guess the power level of the X-ray tube used? 0.02 watts, 0.2 watt, 1 watt, 5 watt, or 50 watts? Fantastic. All right. We're going to look at those results a little bit later. Now let's move to our next question. So here's our second polling question. Oh, I'm only seeing one polling question. Okay. So I think we'll just move right into introducing our speaker then. Sorry about that. So I'd now like to introduce today's speaker. We're very pleased to be joined today by Ming Gao. Ming Gao has over 2 decades of experience in advanced X-ray optics, particularly in polycapillary X-ray optics. He works closely with XOS customers, from leading original equipment manufacturers in the material testing industry to pioneering researchers at universities and national labs, to find the optimal solutions for their application needs. As a globally recognized expert in X-ray optics and their applications, Dr. Gao is active in the analytical X-ray community and collaborates with top scientists on many pioneering research and development projects, including the Pixel instrument on the recently launched Mars Perseverance rover. Prior to his current role, Dr. Gao worked as a senior research scientist at XOS and was the principal investigator for multiple government grants and R&D projects. Dr. Gao, thank you for joining us today. Please get us started.
Thank you, Laura. Hey, good morning, good afternoon, good evening, depending on what area you're calling in. Thank you for attending this event. I would also like to thank Spectroscopy for giving us this opportunity to talk about the exciting technology of polycapillary X-ray optics, and also what critical role it plays in this exciting Mars 2020 program by NASA. So on July 30th, 2020, this year, I don't know if many of you have had the chance to watch the launch of the the new Mars rover developed by JPL. The name is the Perseverance, which is a new rover with 7 scientific instruments on board. And one of the most complicated analytical instrument is planetary instrument for X-ray lithochemistry, which is called the Pixel. That's designed and built by JPL, and it is a micro X-ray fluorescence instrument that can allow a two-dimensional elemental mapping of rock samples with a very fine resolution, around 100 micron. And this is an effort to review the geochemistry fine structure of the Martian surface. So the primary goal, again, of this NASA's Mars 2020 project is to search for signs of ancient microbial life on Mars. And in the previous mission, that X-ray XRF instruments was also launched to do this kind of research work. However, the spatial resolution scale is at a millimeter or even centimeter. So the new Pixel instrument is a great improvement in terms of spatial resolution and also detection sensitivity that will help us to answer some important questions about ancient life on Mars. Okay, so now I will switch it to Laura to give us the result of the first poll question.
Yes, so now we can see that our audience split evenly on 2 of the choices. So half the audience believes that the power level was 0.02 watts, and the other half believes that it's 1 watt. So back over to you, Dr. Gao.
Okay, wow. Great answer, great result. I think apparently half of you guessed correctly, and but between these two, the first one is correct. It's a 0.02 watts. So it's a 20 milliwatt X-ray tube used on this mission. And one of the reasons, of course, for this low-powered X-ray tube used for the system is for this space mission, every watt, or I would say every milliwatt, and of the power and every gram of the weight counts. So this is where the polycapillary X-ray optic plays the important role, that with the very light weight of the instrument and the very low power X-ray source, it will allow the very comprehensive measurement to be done with a great spatial resolution and detection sensitivity. So let's take a look about the structure of the Pixel instrument. So at the center of the Pixel instrument is a polycapillary focusing optic, and it generates a 100 micron, I think it's 120 micron excitation beam that is about 25 millimeter. The optic has about 25 millimeter working distance, which is also critical. That will allow the robotic arm of the rover, of the instrument, to look at the sample from certain distance to make sure that the instrument itself is well protected. So with the use of the polycapillary optic, the X-ray intensity generated, at the sample on the sample. It's about 1,000 times higher than if we just use conventional pinhole collimator. So apparently, if you just use a pinhole collimator of 100 micron, there's no way to carry out such measurement at the speed needed to map the relatively large surface to get the information we will need it. So the milliwatt X-ray source already allow enough sufficient X-ray conduit to be obtained using the high-speed silicon drift X-ray detector to achieve the energy resolution and also measurement speed. The low-watt X-ray source is also essential, just because, as I mentioned, every millimeter in the design counts, and every gram in weight counts, and also every milliwatt in power consumption also counts. So when we look at the structure, you look at the center, this white piece, that's the polycapillary optic. It's surrounded by two energy dispersive X-ray detectors, CCD cameras, the laser pointer to measure the distance, and also the high voltage power supply and X-ray source is sitting on the back, and the system is running at 20 kilovolts. And the reason for not going any higher voltage is because the high voltage power supply unit was the one used in previous mission. It was well tested and characterized, so it's a very safe bet from NASA's perspective. So they decided to use the existing high voltage power supply design, even though it's not the optimal, that 28 kilovolts operation condition is not optimal for the rhodium X-ray tube on board, but it's still just good enough to perform the analysis that is needed for this mission. And this whole instrument on top of this graph here is supported by 6 motorized arm that will move the whole pixel head in the 3D dimension, and that will allow the mapping of the sample surface and at different height, because this one has automatic height adjustment that will allow the focal spot of the polycapillary optic to be right on the surface to be analyzed to give the most precise information for the analysis. So now let's sit back and take a look how polycapillary optic focusing optic works. So a polycapillary optic consists of from submilling to multimilling small capillary channels, and those are just made of glass. So each glass channel is about 5 to 10 micron in diameter. So the physical dimension of the optic is very small. It's in the scale of just a few millimeters to about 25 millimeters, the largest for the current manufacturing status. So the X-rays will transmit through the curved capillary channels by multiple external total reflections. As you can see from this illustration, all the polycapillary channels are curved in a way that each individual capillary is pointing to the same spot outside the optic. So this spot is called the focal point of the optic. So for a full focusing optic, we can see there are two focal spot size on each side. So if you put an X-ray source on one side, and then the optic will collect the divergent X-rays from the X-ray source and then transmit them through the small channels. And then at the other end, all the X-rays coming out of the optic will be focused to the same spot. And that is the output focal point. So the advantage of using this polycapillary optic, as you can see, is that it collects a relatively large solid angle from the source, and then it refocuses them to a very small spot, as small as 5 microns these days. So if imagine without using the optic, the conventional way to get such a small spot is just to use a mechanical pinhole collimator. When you get to micron scales, you are going to throw 99.99% of the X-rays away, and only a very small amount of X-rays will be able to go through that small pinhole, and the intensity certainly suffers big time. So by using the polycapillary optic, you can collect much larger solid angle X-rays from the X-ray source and then refocus them. In that case, the X-ray flux density you can get by using the optic is up to 5 orders of magnitude higher than using a pinhole collimator. So the polycapillary optic is absolutely a game changer for the micro X-ray analysis work, because with the conventional pinhole collimator, as I mentioned earlier, the excitation X-rays you're going to get on the small scale is so low that it's just practically impossible to perform the X-ray analysis with the precision and measurement speed that most research or industry work will need. An important characteristic of polycapillary optic is that it's a broadband optic. So it transmits X-rays of all energies in the range from about 100 EV to 50 keV. As we will talk later, above 50 keV, the X-rays, the transmission efficiency will significantly drop to the point that it just becomes practically not feasible to use it at that energy range. So the polycapillary optic has a monolithic structure. So it's a one-piece device that will make this optic very compact and robust. So back to the Mars Rover program we talked about, as you can imagine, during the launch and more importantly, when the Mars Rover is going to land on Mars surface on February 18th, 2021. So it's about 80 days from now. The landing part is the most critical part, just because all the very sensitive scientific instruments is gonna will be tested. How they can tolerate that impact at the landing on the Martian surface. So among those critical instrument device on board, the polycapillary optic is actually considered more robust than others, such as the X-ray source, X-ray detector, some of the sensitive electronics. They are certainly more subject to this kind of landing impact. In comparison, the polycapillary optic is considered much more robust. So now with the successful launch back in July, the team is anxiously, waiting for the landing of the rover, which is certainly more critical. As of last week, I got an update from JPL that they just did another test on all the instruments on board, just to look at the connection, the operation conditions. Everything has been well, which was a great news. But I think everyone is anxiously wait for February 18, 2021 landing of the rover, and we certainly keep our fingers crossed for that. Okay, now let's take a look at the fundamentals of how polycapillary optic works. As I mentioned earlier, X-ray transmits through this curved capillary channels by external total reflections. So the X-ray total reflection is very different from the total reflection for visible light, because in X-ray energy range, the refractive index is less than 1, while in visible light range, the refractive index is greater than 1. It's, for example, glass is in the range of 1.4, 1.5. So this is why for regular fiber optic, let's see, for communication use. So the fiber optic, the total reflection occurs in the core of the glass, because the total reflection occurs between the glass and air. So the light transmits inside the glass core and not in the air. But for X-ray region, it's totally opposite. The X-ray transmits in air, while the total reflection occurs at the surface when the X-ray hits from air to the glass, which makes off the capillary. While the refractive index is less than 1, it's just very slightly, because that parameter is a complex, and it has expression as it shows in this formula. And delta and beta describes the dispersive and absorptive aspects of the material. And their value can be calculated from atomic scattering factors that, you have a table that you can just use. So after all the calculation, we can get the critical angle for total reflection of X-rays, which is expressed here. And on the right, I gave some examples, like for glass, which it's a silicon oxide. The critical angle is anywhere in range from very small, like 0.08 degree to close to 1 degree at very low energy. So you can tell the higher the energy, then the smaller the critical angle will be. And actually, I would like to show you this slide first to talk about this critical angle formula. After all the calculation, it actually ends up with a very simple format. It's just 30 over the energy of X-rays in keV. So for example, at 8 keV, this critical angle is around 3.8 milliradians, around like a quarter degree. So when the energy goes higher, the critical angle decreases, and at 17 keV, it will be around 0.1 degree. You can see those values are very small. Going back to here for glass, silicon oxide, this critical angle, even at the very low energy, it's still below 1 degree. So if you use other material, like if you do a coating on the surface of polycapillary optic with the material like a gold, you can increase this critical angle, but still, at a very low energy range, it's below 2 degrees. So this is the factor that makes it difficult for X-rays to satisfy this total reflection conditions, especially when you bend the capillary channels. So now we will see how the X-rays transmit through a curved capillary channel. So on top, let's see, if you have a curved channel with a large size, this orange ray or this, let's see, the green rays, they come in at a very small incident angle, and they will be able to go through this curved channel by multiple total reflections. However, for the red color ray, it comes in at a larger incident angle, and when it hits the wall of the capillary, the incident angle will exceed the critical angle, so the photon will get killed. However, now if you add another layer, here I just use an example, just add one layer. Of course, in reality, you have thousands of layers there. So this way, when the X-ray comes in, it will hit the wall way before it gets to way before the incident angle gets too large. It will hit the wall with the angle smaller than critical angle, and then in that case, it will be able to be totally reflected by the surface. So this is just to show the importance of small channel for polycapillary optic. This is also why at the beginning I mentioned there are millions of channels in a structure with only a few millimeter outer diameter. So you can see the density of capillary in this structure is quite tremendous, and you can only see those fine structures under scanning electron microscope. So this is where I will show those structures. So on the left, that's just the microscope structure of the cross-section of a polycapillary optic. This one has an outer diameter around 5 millimeter, flat to flat. Then the channel size of this one is about 10 microns. As you can see, there's very large open area, which is critical because as I mentioned, the X-rays transmit through in the air, and you want maximize the open area of the polycapillary optic. But at the same time, you want to make sure the wall of the capillary is thick enough to maintain the mechanical strength of the device. So it's not easy from manufacturing perspective, to maintain this high open area. And again, this open area also depends on the structure. When you get when the channel size gets very, very small, it will be very challenging to get anything close to 80%. It will drop to more or less like 60%. But still, it's quite a large area that will maintain the high performance of the device. The shape of the optic needs to be precisely controlled to the single micron level, because the X-rays will follow certain trajectory. We have a powerful simulation tool that will help the optic design. If the profile of the actual optic differs from design by just a few microns, then the X-rays will be off the design trajectory and get absorbed by when it hits the wall, it just won't get the total reflection condition, and the photons will just get killed or absorbed by the glass wall. To maintain that high transmission, the surface roughness needs also to be well controlled to make sure the X-ray total reflection occurs according to the design and simulation. Again, all these factors contribute to the high transmission efficiency of this polycapillary optic device. So now we take a look at the different types of polycapillary optic. This one is what referred to as collimating optic or parallel beam optic. So basically, the device will collect X-rays, the divergent X-rays from the source, and just convert it to parallel beam. So if you think of this, you can just think of a full focusing optic. If you just cut it in the middle at the largest outer diameter, it becomes a collimating optic that will give you a parallel output beam. Of course, there's no absolute parallel beam. Here we're talking about a parallel beam with a very low divergent angle, which is energy dependent. We're going to talk about those parameters later when we get to the optic characteristics. So at this point, the largest polycapillary collimating optic XOS can make is around 25 millimeter. This is just simply limited by the optic manufacturing facility and the instrument. But we are continuously improving our manufacturing capacity, and hopefully to make larger polycapillary optic. And I think the goal is in the next 5 to 10 years, we would like to increase this to about 100 millimeter. And the output beam brilliance is improved by up to 2 orders of magnitude compared to conventional solar slit, because without using optic, it's the only way to get the parallel beam is to use this conventional solar slit is basically stacked metal foil that will just eliminate all those divergent X-rays and only allow the straight X-rays to pass through. So the efficiency is extremely low. And so the polycapillary optic, of course, will have an enormous advantage comparing to the conventional technology. So if we turn a collimating optic around, and then it just becomes a half-focusing optic. So if you have a parallel incident beam coming in and the polycapillary optic will accept them and then focus the X-rays to a smaller spot. And this is the application mainly used at the Synchrotron facility, which they have very parallel incident beam coming in, and the half-focusing polycapillary optic will just be able to collect them and then focus to a very small spot for different applications. So here are just some pictures of raw optics on the left, and the optics packaged in the metal enclosure in the middle. And on the right, that stainless steel tube sticking out with the gold plating, that's the polycapillary optic used on this Perseverance rover. I mean, on the Pixel instrument that I mentioned earlier. And this is when we ran the final test at XOS to do the optic characterization, working together with NASA team, with JPL team. Okay, so again, another fundamentals of the polycapillary optic technology. As I mentioned, all the individual channels point to the same spot. So the focal spot of the polycapillary focusing optic is determined by this simple formula, because as you can see, the X-rays coming out of each individual channel has a local divergent angle. That's just, and this divergent angle is determined by the critical angle. So each of them look at the same spot, and the size of the focal spot size is basically determined by how much the beam divergent through the focal distance of the optic. So, for example, at about 8 keV, this critical angle is around 4 milliradians. So if you have an optic with 10 millimeter focal distance, a simple calculation will give you about like 40 micron focal spot size. So you can always use that formula to estimate the how small the focal spot is, and also at any given X-ray energy. Of course, we have simulation tool that will calculate this more precisely. So we run the optic design with the different application requirements from the customer, and we can get a very accurate estimate on what focal spot size one can get from a very specific optic design. And same formula can be used on the input side of the optic. And so the input focal spot size is what we refer to as a field of view of optic. As you can see, because of the divergent angle from each channel is relatively small. So this field of view is very small. Depending on the optic design, it can be anywhere from a few tenths of microns to a few hundreds of microns. So this is why for optic to work efficiently, we would like to couple it with a microfocus X-ray source, just because so that the X-ray source will be within the field of view of the optic. If you use a very large X-ray source, of course, the optic will only be able to see a very small portion of the source. In that case, the efficiency of the optic will drop very quickly. So the key performance parameters for a polycapillary focusing optic, we mentioned earlier, there's a focal spot size determined by this formula. We have transmission efficiency, which is the ratio of output X-rays to those captured at the entrance of the optic. So this transmission efficiency can be in the range from a few, a single-digit percent to up to like 50%, depending on the energy and optic designs. However, when you look at the performance of the polycapillary optic, you can't only look at the efficiency number itself, because another important parameter is the geometric collection solid angle. So it's the combination of the geometric collection solid angle and the transmission efficiency that determines the output X-ray intensity. For example, you can have an optic with very long input focal distance, and in that case, your transmission efficiency can be very high. However, your collection angle is small, so at the end, your output intensity may not be as high. So this formula here, the product of geometric collection solid angle and the transmission efficiency, we refer it to as effective collection solid angle, which is directly related to the output X-ray intensity of the device. And then we also define the X-ray flux density gain. So basically, between using an optic and using a conventional pinhole collimator, what the X-ray intensity ratio you are going to get. So as you can see with the pinhole, of course, the collection solid angle is very small when you need a very small beam spot. This is why the intensity gain can be as high as 4 or 5 orders of magnitude. However, for end users, that they can define this base case differently, because as we can see, this the collection solid angle for pinhole is dependent on how far you put the pinhole away from the source, right? So if you put it at 100 millimeter, 200 millimeter, then the intensity is low, but one can argue, hey, I can just put this pinhole right against X-ray source. So in that case, sure, the flux density gain of optic will drop. However, we all know, sometimes it's just practically very challenging or impossible to place this pinhole very close to the source. So whenever we quote customer or we talk about flux density gain, we always define what the base case is. And the customer can always calculate back if they want to look at the base case differently to figure out what's the real benefit they're going to get. And comparing to, either you spend money on using this fancy optic, or you can just use a very cheap pinhole collimator. If there's any way you can get the pinhole close to the source to get the performance you need, you should definitely do it. It's only when you cannot put those using this conventional approach to get the performance you need, and then the optic will definitely benefit for your application. And this is a curve to show how the transmission efficiency changes versus energy, and also for versus different X-ray source size. As I mentioned earlier, the high transmission efficiency of a polycapillary optic, requires a microfocus X-ray source. So here you can see with the between 50 micron and the 500 micron source, the transmission efficiency, changes dramatically. So this is why the use of a microfocus source is critical for polycapillary optic, and just to fully utilize the benefit of this technology. Well, looks like we are running behind on time, so I need to speed up a little bit here. So again, this is about polycapillary optic characterizations, how we measure its performance, how we get all those performance parameters mentioned in the last slide. So this is a direct beam mode that you have X-ray source, optic, and the EDS X-ray detector. However, whenever you run this kind of measurement of optic, you need to put a filter, primary filter between the X-ray source and the optic, just because otherwise the X-ray intensity is just too high for the detector to handle. I don't want to go to the details. Basically, you just need to move your X-ray source in XYZ direction to optimize the output intensity to get the optic to be fully aligned with the source, and then you can measure the output intensity and also the output focal spot size. Okay, now we get to our next poll question. Laura?
Yes, so for all of you, yes, thank you, Dr. Gao. For everyone in the audience, once again, we have another polling question for you, and we would like you to click directly on your screen to enter your answers. And here's that question. What is the sensitivity of optic alignment? 1 micrometer, 10 micrometers, 100 micrometers, or 1,000 micrometers? So once again, click directly on the screen to answer the question. So what is the sensitivity of optic alignment? 1 micrometer, 10 micrometers, 100 micrometers, or 1,000 micrometers? All right, let's pull up those results very briefly. And everybody chose 1 micrometer. All right, so back over to you.
Thank you, Laura. Well, actually, the X-ray optic is not that sensitive to this alignment. So the correct answer should be around 10 microns. So thank you for all to participate and to answer the question. As I mentioned earlier, you need to, the field of view of optic is very small. You need to do careful alignment to achieve the optimal output intensity. However, actually, fortunately, the sensitivity is not at that 1 micron level, because that would make it very difficult from practical point of view, to maintain this alignment during the use of the instrument. So the correct answer should be around 10 microns for this alignment sensitivity. So again, to continue the optic characterizations, and then here is how you measure the optic performance using X-ray fluorescence mode. So you put the detector. This is the way most of X-ray instruments use the configuration. So the X-ray, the detector is looking at the sample to look for fluorescent signals. So you can, for the alignment purpose, it's the same that you can do the, oops. I think we have some technical difficulty here. Okay, I got part of the slide back. I don't know why it doesn't show the whole thing on my screen, but it's okay. So again, the alignment procedure is the same as the direct measurement mode I mentioned earlier, and the alignment sensitivity is certainly, it doesn't change here. but it just allow a more flexible measurement for the users, because when you put your system together, normally you don't put the detector behind the optic to only look at the optic. You want to look at your samples to see what you see from it, and then you can certainly characterize your optic alignment or performance this way. This is just the explanation of the use of primary filter, that basically with a given anode material of the X-ray tube, if you use the primary filter wisely, you can get multiple peaks that will help optic characterization. However, this technique is only useful for the direct beam mode in X-ray optic characterization that we use at XOS. For end users, normally you only use the primary filter to improve your detection sensitivity for certain elements. So it's a different purpose there. This table just summarizes the X-ray performance, and you can see the focal spot size can be as small as 7 microns at the 17 keV. When you get to higher energy, for example, if it's a rhodium K alpha at the 20 keV, the spot size can be as small as 5 microns. And this is just table we give examples on any given anode material and energy. So you can see the working distance varies, and it's then the focal spot size is basically proportional to the working distance. This is why if you want to get a very small focal spot, then the working distance, it just has to be small. This is governed by the physics behind the technology. The performance parameter for high focusing optic is similar definition, and here just list all the numbers. For collimating optic, it's slightly different, because when you compare the intensity of output X-rays, you cannot just you look at the quality of the output beam. You cannot only compare the intensity, because when you try to get the parallel beam, you also need to find out how parallel and what divergent angle you're getting. So if you compare to an X-ray output without using the optic, if you want to get the same divergence or same parallel, how parallel the output beam is, then you need to put your pinhole at the very far away to get the same quality of beam. And here's how the intensity is defined. So you can see the larger the output beam size you will need, then the higher intensity X-ray intensity gain you will be able to get. So that makes sense. Just imagine if you don't use a polycapillary collimating optic, if you want to get a very large parallel beam, you just have to put it so far away, to get the divergent angle to the level you would like. So in that case, the capture angle is certainly very small. So it's basically with the pinhole collimator, your capture angle equals to the divergent angle you will need, which is normally very small. It's less than 1 degree.
Dr. Gao, just another quick time check. We have about 5 minutes till the top of the hour.
Okay, thank you. Yeah, I will definitely keep that in mind. So just this is just a list of different polycapillary optic applications. So we are just go through each of them very quickly. Micro XRF, this is one of the most popular and the most successful applications for the technology. As you can imagine, if you want to do XRF analysis on small features, polycapillary optic focusing optic is the way to go. So here are some examples for the application. Microelectronics, particularly plating thickness measurement. And this has become a very common industrial application, not only from technical perspective. It also helps the manufacturer to save money when they are able to measure this plating thickness on the small scale very precisely and very quickly. And then material analysis in the middle one is just this is an example for two-dimensional elemental mapping to review certain structure and the characteristics of the material. It can be used in semiconductor, solar cell, like steel industry, air particulates, many of those. Forensics this is an image for gun residue powder analysis. So all this small feature analysis is critical for the application where the polycapillary optic plays an important role there. I'm going to just go through this quickly. More micro XRF applications, life science, geoanalysis. This is the one actually the Mars rover is going to do, is just to look at the mapping of different elements. The previous mission only looked at the bulk analysis, and with the new pixel instrument, it will be able to map the surface of the rock and give them the scientists better chance, to look for the signs of ancient life. Art conservation is another one that I don't think we have time to talk details. I'm going to skip this one. Micro XRF SEM. This is a very unique application. I think many of you may have experience to use scanning electron microscope, which is a very powerful imaging role. It has its own EDS capability that will allow you to do elemental mapping. However, with the electron probe, the detection sensitivity is not that great, especially for transition elements. So one can put an X-ray excitation that coupled with the polycapillary optic to provide micro XRF capability to the system, because over here you already have the EDS detector, you have the sample control, you have all the stages, you have the cameras. So all you need is a different excitation source that can help you improve the performance of your existing instrument. So the add-on X-beam, what we call, or flex beam, it's a polycapillary optic coupled with the source in one piece, added to this system to extend the analysis capability. It's another very successful application for the technology. Synchrotron applications. I mentioned earlier, high focusing optic is mainly used for synchrotron facility because they have a parallel beam coming in, so you can just use a high focusing optic and to focus on the sample for small sample analysis. It can be micro XRF, can be micro X-ray absorption, spectroscopy. So many of those. There are many publications. Here is another unique application. It's a wavelength dispersive spectrometer. Comparing to conventional approach that you use a curved crystal to realize that function, you can just use a collimating optic to convert the fluorescent X-rays from the sample to a parallel beam and then just use a flat crystal to realize the same functionality. However, with this polycapillary optic approach, your spectrometer can be made much smaller and much cheaper. So here, let's just give an example of a commercial WD spectrometer that they mounted on scanning electron microscope. I'm going to skip this one to talk about the WDS benefits. This application is a microcalorimeter. Again, and a polycapillary optic, focusing optic can be used to collect. This is when the optic is used again on the detection side, like the WD spectrometer, that they collect X-rays from the sample and convert it to a small spot. In this case, the microcalorimeter X-ray detector is a superconducting detector that has very small active detection area. So by using the optic, you can improve the effective collection efficiency of the detector by a factor of 100 to a few hundred. That's a confocal XRF that I will just jump right into next one since we're going to talk about confocal. So this is when you use two polycapillary optics, one focusing optic on the excitation side, and then you use the second one, the detection optic in front of your energy dispersive X-ray detector. So the two focusing optic will form a very small spot in the 3D space. So with this geometry, you will be able to do actually under-surface analysis as long as the matrix of the material is light enough to allow fluorescence X-ray coming out. And this has become a very popular and successful, in art preservation applications, that you will be able to look at the distribution of elements underneath the artwork. Again, that's just another confocal XRF application, and you can, by using the polycapillary optic on the detection side as well, you will be able to reduce the background significantly and improve your measurement results. Just a quick discussion on what if you use a large source with polycapillary optic. In the past, we always tell our customers, hey, you only want to use a small X-ray source to make the optic very, very efficient. Then if you have a large source, the chances you may not be able to benefit from using the polycapillary optic. Well, if you look more carefully, we will see in most cases we found when the customer has a large X-ray source, if they try to get a very small spot using a pinhole collimator, in theory, yeah, you can get the very small spot. However, in practice, if you want certain working distance, it's very difficult to get the spot to what you want because the X-rays will diverge right after the pinhole. And in that case, the pinhole is certainly just it's like an imaging device that you will get the image of your X-ray source that, may not be practically useful for your small beam requirements. So we found in that case, you can use a high focusing optic to get a focal spot and also get the working distance you will need for your application. Here, we're talking about X-ray imaging, just to use a conical optic, polycapillary optic, to realize spatial resolution from, from a very small sample. If your imaging detector, for example, your CCD X-ray camera, it doesn't have the resolution you need, you can use this conical optic to improve your imaging resolution and the contrast. X-ray diffraction, I'm going to go through really quickly. Again, it's a parallel beam, on the sample. So in that case, your result won't be affected by any sample height variation. This is very useful, especially for inline applications that you have a flying sample going through, and you cannot avoid the sample height variation. So a parallel beam XRD is the way to go. This is just one example of those. This is for texture measurement of superconductor tape that I have to skip because of the time restriction. Okay, just a few success stories of the polycapillary optic technology. First, certainly the Mars rover, the Pixel application, and that's for research. As I mentioned earlier, the polycapillary optics are now widely used for industrial applications. So it's not only for research, sometimes for fun, and this is really for getting the financial impact and the financial benefit by allowing certain measurements to be done with the precision and with the high speed you will need. As I mentioned earlier, plating thickness gauge is a perfect example to help the device manufacturer who needs to plate their the microelectronics with the very expensive metals, mainly like a gold or palladium. So in that case, they can control their plating process to minimize the use of material, and at the end is a big money saving, so big financial impact. This is the flex beam product offered by XOS. So it's basically a micro-focus X-ray tube coupled with the optic. So in this case, the optic is pre-aligned and locked, so the customer doesn't have to deal with all this tricky task. We call it just a turnkey subsystem. It comes with a controller. So you make connections, you turn on your controller, and you will get the focused X-ray output right away. And that's the small version, what we call the mini beam, that XOS is going to launch very soon. So this is a 12-watt system, and the previous showing a flex beam is a 50-watt source. So this is a more compact system for customers who will need a more compact solution. Okay, here is just a quick summary. I will just let you read it through. But more importantly, I just want to go back to the very top topic we are in today. As for the Mars rover application, the Pixel instrument is actually it's definitely benefiting from using the polycapillary focusing X-ray technology. It allows the mission possible, with a low-powered X-ray source, very compact, X-ray instrument, the Pixel, that will be mounted at the very end of the robotic arm if you can just search online to look at the rover picture. So that's definitely one of the most exciting scientific instruments, on the Mars rover. With that, I would like to thank everyone for your attention. I'm sorry for being behind on time. I hope you enjoy the webinar, and hope to hear some questions from you.
Thank you very much, Dr. Gao, for that fascinating presentation. So given the time, we won't have time to do a live question and answer period today, but if any of you have asked a question, someone will follow up with you offline after the event to answer your question by email. So I again would like to thank Dr. Gao again for the talk today, and I'd like to thank everyone in the audience for attending and participating in our event. And I'd like to thank our sponsor, XOS, for making today's webcast possible. You'll receive an email alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.